Today, I'm going to talk about Balsam, a workflow manager developed at the ALCF. Balsam is a particularly useful tool for managing a large number of application runs on an HPC system like Theta. So if you need to achieve high throughput on our systems and track the status of your runs over an extended period of time, you should consider using it. First, I'm going to review the standard way of achieving higher throughput on our systems, which is simply by launching multiple applications in a single shell script submitted to Cobalt. So in this example, we have a small allocation of 5 Theta compute nodes shown on the right-hand side. And suppose that we want to run several instances of an application shown here in this variable, myApp. So it's crucial to remember that your Cobalt job script is executing on a mom node, which has a completely different architecture from the compute nodes and is shared by all users on the system. We then launch our applications from the mom nodes onto compute nodes using the apprun command. So here, the first apprun command launches a single node job with 64 ranks, one for each core on the KNL. We launch with our first hypothetical input argument and ensure that all the output is directed to a file called run1.out. And notice this trailing ampersand here is very important, which places the app run process in the background, and then we sleep for 1 second. We launch a second application in a very similar fashion, this time across 2 compute nodes with 64 ranks per node, and output is directed to a separate file. And we can do this again for our final 2-node job. So in this way, we've filled up our 5-node allocation with 3 application runs. Notice that it's very important to sleep between consecutive app runs to avoid overwhelming Theta's application placement system. And you want to issue a wait command at the very end so that your job script blocks on the completion of all of these application runs. This type of Ensemble job script is documented on our user guides at the link below. So what do we really mean by workflow? There's often considerable ambiguity about what constitutes a workflow. I would argue that the shell scripting approach we just saw is already a good example of how you can manage a workflow consisting of maybe several hundred runs. In situations like this, the bash scripting language is perfectly capable. After all, we can use looping and other programming constructs to set up a parameter sweep. We can control where the output of each run is directed. And by keeping an organized directory layout and composing a few scripts to check on the status of our runs or submit new runs, we really have everything that we need to get our science done. Furthermore, Theta allows up to 20 jobs queued at a time. So with traditional larger scale runs, say on the order of 1,000 nodes and 10 hours, you could see in this example calculation, it's very easy to burn through a large allocation on our systems without really resorting to any specialized workflow tools besides the scripts you're already comfortable writing. Some issues do arise, though, when we start running larger numbers of applications, and those applications are done at smaller scales. So the same hypothetical allocation might span 10,000 runs instead of just 100. And here, instead of just launching a fixed set of runs at the beginning of our shell script and waiting till they all finish, it becomes very likely that we also want to run jobs one after the other. In other words, we're not just packing runs across compute nodes, but across time as well. And this is particularly important if there's a significant variance in runtime. Otherwise, we're going to end up waiting on straggling jobs to finish and wasting our precious idle node hours in a job. So this is not trivial to achieve in a shell script. You also need to consider that we need to keep track of which tasks have finished, because it becomes increasingly likely that some runs will be cut off on a job wall time boundary. So workflows like this start to require a human in the loop to process partial results before submitting the next job. And this can get very out of hand when we go to workflows involving maybe even tens of millions of application runs. And we do see workflows of this scale where we're running several single node jobs that maybe only run for a few minutes. And here clearly the effort required to manage a project of this same size becomes much larger than just for a few hundred runs. And simple shell scripts are no longer really enough to keep track of your campaign. At this point, you would probably switch to a more sophisticated scripting language and write your own tools to handle this complexity. And often people do this with Python or similar languages. But you'd have to address a lot of challenges here and spend considerable effort addressing limitations like the maximum number of queued jobs in our system being 20. So you would have to pack many runs per node. You would have to come up with a strategy for multiple program data and multiple data execution. So it's not necessarily trivial to do this, especially when you're considering running several jobs across the lifetime of a job. And then it would also be important here to track errors and timeouts and handle them appropriately. So Balsam is a system that kind of handles these issues by allowing you to submit unlimited application runs to a task database that belongs to you. By submitting your application runs here, the system is able to optimize the fashion in which it allocates resources and runs your applications across those resources. So Balsam consists of a few components. The service is there to automate queue submission for you, and the launcher is a pilot job mechanism, which actually pulls tasks out of your database and runs them in a load balanced fashion. The launcher is resilient to task level faults, so you catch errors in your applications, and those are tracked in the database for you. And it provides mechanisms for automatic retry or handling of timed out jobs and even failed jobs. The launcher runs completely unmodified applications, and so it's compatible with pretty much any existing code or even containerized applications can run with Singularity on our systems. And the advantage of tracking all of your workflow metadata with Balsam is that the status of your jobs and statistics such as throughput are available at a glance by interfacing with the Balsam database. Balsam's been in production at Argonne for quite some time now. It's available on Theta as a module, so the module load Balsam command will make the command line tools available to you. And we have documentation available as well through the Argonne user guides. Balsam's been pretty broadly used across several science domains. So here we're looking at usage over a span of 1 year from September 2018 to September 2019. And in this time, we saw that Balsam was used for about 125 million Theta core hours. And this was used over 28 projects. Some of the dominant ones here are material science workflows. So these are several projects doing various simulations with applications like NWChem or VASP. And Deep Hyper is another major usage of Balsam. This is a hyperparameter optimization framework that's used widely on our systems to find effective deep learning models for various scientific tasks. So before getting into a detailed walkthrough of how you can use this on Theta, let me quickly highlight some of the Balsam components so you get a better understanding of where things are running and what components are responsible for actually running your work. So the database is where you begin your interaction with Balsam. There's a BalsamJob table, which contains one row for every task that you want to run. The details of creating this database are completely handled by the Balsam command line. So with this single command of Balsam init, you're able to set up a Balsam database directory at the given path. The Balsam launcher then pulls tasks from this database as indicated by the dashed line, and it can then launch applications onto available compute nodes within a job in a couple of different ways. So the MPI job mode is sort of very closely mapped to the Ensemble job script we saw in the beginning. So here we have a very conventional application launch where one app run or similar command is launched for each application in your database. The serial job mode is a little bit different in that it can pack several tasks per node. So when you have a large number of applications that don't use MPI and you may want to run 4 or 16 per Theta compute node, the serial job is the way to go here. The big advantage of using this job mode is that there's only one app run running on the mom node and handling all of your tasks in a single runtime. So the Balsam service is then the interface to the Cobalt scheduler to get these things running. You typically will use the Balsam submit launch command to render a template job script that's then submitted on your behalf to Cobalt. You can also use the Balsam service to automate queue submissions. And a typical workflow with Balsam starts by populating your database with runs and then tracking the progress of all of these runs. So in the beginning, you might want to use something like Python and the API that Balsam provides to define a large number of runs. This example shows this Balsam job constructor, which allows us to define tasks. I'll go into much more detail on this later on. And we might use Python to crawl over a large directory of inputs. And for each input that we find, we can create a Balsam job tasks and save it to the database as shown in these last two lines. So this is typically how we get our work into the database. And then we use the submit launch command, which is very analogous to the qsub command that you already know on Theta. And we request here in this example 2 nodes for 10 minutes on the debug queue. And most importantly, we specify the job mode as the last argument shown here. So we can track the status of our jobs in this workflow using the Balsam ls command. In this case, we can filter for failed jobs and use the history argument to get a traceback from any failed jobs. Or in this case, we're just getting the tail of the error stream from each of our tasks that ran under this database. The API is also very useful for making more flexible queries than you can from the command line. Here we see that we can filter for timed out jobs using this filter construction on the Balsam job, and then we can get a list of working directories of our timed out jobs. We also have convenience functions for visualizing things like throughput. So in this chart, we've created a plot of the number of tasks that are running at any given time. This is shown by the orange curve, and this is a good way to check the utilization of your job, and that you're actually running something on each compute node for as long as the Balsam job is running. And then here the green curve shows our throughput as the number of finished tasks over time. So as an example of real world usage here, we see the throughput and utilization from an Argonne data science project, which was involved with looking at free energies of several molecular crystals. So here we ran over 20 million hours of DFT with the FHI AIMS application. These were all MPI job mode runs under Balsam. So each run was a single app run. And we scaled this to over 90% of Theta, and we, in the end, ran several million tasks. And there were up to 5 simultaneous jobs running at a single time. So here, this blue curve shows the utilization as number of running jobs. And we were running in increments of 802 nodes. So you see that by running up to 5 of these, we were using 4,010 nodes of the system. And the great advantage here is that all the jobs are cooperatively pulling tasks from the database. So there's no need to separate which tasks run in which jobs. That's automatically handled for you. And the Balsam launcher guarantees that each task is processed exactly once. So one other way that Balsam is commonly used that I'll mention is that applications can actually be submitted to the database from anywhere, including compute nodes. So in many instances, we have search applications where some master process running on one of the compute nodes is actually sampling configurations, and for each configuration, submitting a job to the database to run on other compute nodes. So in this way, we can actually dynamically generate runs in the span of a single job. This mode of usage is also pretty common with Balsam. A couple of the big ones are the deep hyper framework. So as I mentioned, this is used for hyperparameter search and neural architecture search for deep learning models. In these cases, the search job itself is commonly very compute intensive. So it runs on a dedicated compute node and generates candidate models to run on the other compute nodes in a job. LibEnsemble is also a very similar idea of a generator type job, which is producing points in an ensemble to run in other simulator jobs within the same ensemble. So with that, I'll start on a walkthrough to actually load up Balsam on Theta and go through some simple command lines so you can get a feeling for using this. At the end, I'll show some references to tutorials that are a little bit more in depth so you can go through and actually start to write your own workflows using Balsam. So on Theta, we want to start by loading the Balsam module. This will set up your path to include Python 3.6 and give you the binaries to the Postgres database that's used under the hood. The Balsam command line consists of several subcommands under the Balsam parent command. So if you just type in Balsam, you'll see a list of the available subcommands to you. We want to start by creating a new database for our project. So in this case, you use Balsam init and you give a path to a database. You should see this success message showing that a database has been created. Once you have a database, you use the Balsam activate command, which needs to be sourced either with the source keyword or with a leading dot. And what this does is actually starts the Balsam database if it's not already running and sets an environment variable to point future Balsam commands at the particular database you're running. And this way you can also switch context between databases. Now, the first thing to do with our database is actually define the application we want to run. With the Balsam app command, we are able to register an executable and give it a unique identifier. So here we're creating an application called Say Hello with the executable of echo hello. So this is just the normal bash built-in command. And we see here that the first application has been added to the database in this fashion. We then use BalsamJob to add instances of this application or specific runs with command line arguments tailored to that run. So here we'll create a job called test1 under the test workflow, which I'll explain shortly. And you can see that we're using the Say Hello application with the args world1. And then we can go on to do this in a loop for several other indices and create an ensemble of 10 jobs here. So the confirmation that you should see on the command line will show you several details of the run you've created and fields that are adjustable to you. So most importantly, you can see that we've selected the Say Hello application with the arguments world1, and then the executed command is just the concatenation of that application with the arguments. So you can see that it's going to run the bash command echo hello world1. And then we repeated this for several other applications. So looking a little bit more closely at the fields available in a Balsam job, we can see that there are tags for the name of the job. This is an identifier that should be unique together with the workflow. And the reason for this is that jobs are placed in working directories according to this scheme shown here at the top right. The working directory is created under a workflow directory with the job name as a subdirectory and a short piece of a unique identifier appended to the end of it. So name and workflow are very useful for organizing your jobs in a large campaign. You often have some way of grouping related runs under the same workflow and different runs with different names under that workflow. The description field is completely optional. This is just any text that you want to attach to a job. You can also override the working directory creation by specifying your own custom work directory if you have your own scheme for where data should live and where applications should be running. We can also attach arbitrary JSON data to each Balsam job. And this is particularly useful when you're parsing results as part of your Balsam workflow. You can actually store any kind of data that's JSON serializable in the Postgres database by attaching it to your Balsam job. And you can later query this data and collect results by name and by workflow. So this is quite a useful technique. Balsam jobs also have constructs for setting up dependencies between jobs. So the parents field allows us to create DAGs or directed acyclic graphs of jobs where a particular child job will only run when all of its parents have finished successfully. There are also fields to specify where data can be staged out or copied to some external location at the completion of a job, or staging URLs that allow us to bring in data before a job starts running. We can also control with these input file patterns what outputs from a parent job are visible to the child jobs. So this combination of fields allows us to compose fairly complex data flows with particular files moving from parent jobs to child jobs, and data coming in from external sources as well as being staged out to some other location where you want your results to go at the end. Finally, most important is that the executable is controlled obviously by our application, and the command line arguments to that executable are set on the job as we've seen. But there are several other parameters that let us control how an application is actually run. So environment variables can be used to set the particular environment that's used at a task level. You can also set environment variables globally for a particular application. We can attach pre and post processing scripts to an application so that the same steps are run immediately before an application is invoked, or afterwards to, for example, parse results or take some special action on a timeout or error to restart the application. And we can control the number of MPI ranks and ranks per node that an application runs with, as well as various threading settings. So pretty much any setting that you could pass through to app run, if you are writing a script yourself, can be set on the Balsam job. So once we've got our job set up, we want to frequently check what's in our database. Again, the Balsam ls command is used most frequently here. Without any arguments, we get a tabular view of the jobs in our database. And here you can see that those 10 testing jobs that I showed at the beginning are actually populated in the database. And the right-hand column of state shows that each of these jobs has been created but not yet run. We use Balsam submit launch, as I mentioned, to submit the job to the queue. Here we're going with the MPI job mode, and we see a confirmation showing the actual shell script that was generated and submitted on our behalf. So these shell scripts go under the queue submit subdirectory of our Balsam database directory, and the template that's actually used to generate these scripts is customizable. So suppose that you wanted to change how we are setting up our job environment, perhaps setting some environment variables that we want to be globally available in our run. We can do this by referring to the file that's set in our job template under the Balsam settings in your home directory. So in this case, this is going to be preset on Theta to this theta.cobalt scheduler file. And we can take a look here and see that before the Balsam launcher is invoked in our job, we have space to insert pre-run commands. So again, this can be setting environment variables or copying data to local storage. So this is a flexible way to do that before your job actually starts running. Eventually, if everything runs successfully at the end of, after waiting for this job to go through, we can check Balsam ls again, and we should see that all of the jobs in our database have advanced to the state job finished. So this tells us that everything was successful. And you may be wondering where output goes, and this is always written out to the data subdirectory of our database. So Again, working directories are created according to the job workflow and name, and this all happens under the my project/data. So looking under this test workflow directory, I can see that my 10 directories for each job name have been created here. There are several other things we can do from the Balsam command line. For instance, we may want to modify the state of a job after it's already finished. In this case, we can use Balsam modify with a few characters uniquely identifying the job ID and alter any field on the job. So here we're resetting that job state to restart ready. And what this means is that the application will be able to run again. So this is useful to maybe tweak some parameters in how your application works and run it again. If you need to do this for a large number of tasks, it's usually much more convenient to use the Python API. So here I have the similar example where we actually start a Python shell, import the BalsamJob object, which allows us to filter. And here we're querying for jobs that run on less than or equal to 100 nodes and that are finished. And then we update those jobs to restart ready so that they can run again. Again, I'll show quickly that we can populate jobs in the database. So this is the same slide that you saw earlier, but now I can go into a little bit more detail. We define here a prep job function to create a Balsam job, given a name, workflow, and path to some input file. So in this case, we're creating a job that will stage in an external paths. So this is an XYZ file that is going to get copied into our working directory for an FHI aims calculation. We want this to run on 64 ranks and a single node. So the number of nodes defaults to 1. So we're just setting the ladder parameter here to 64. And we want to use the CC depth option of AppRun to bind one thread to each processing element on the node. And that's achievable here with these last two flags. Finally, we can use this function really however we want. In this case, we're using OSWalk to search a directory for these XYZ files, which are going to be the input to our simulation. And for each match, we're going to create a job with a name and workflow that identify the location of the file and the path to the file itself. Another thing we can do with the API is create tags, as I mentioned. Here we're setting up some dependencies between jobs, and the dependencies are shown in the plot here. So we have some parent job A, which fans out to 3 children, B, C, and D. And when all of those are finished, the child job E will take those, the outputs of the 3 intermediate jobs as input for some final reduction step. So this is a pretty common pattern in workflows, and it's very easy to write with the Python API in Balsam. So here you can see that we've set up the jobs in the beginning of the script, but focus your attention to the last 3 lines. Here we loop over the 3 middle jobs, B, C, and D, and we create a dependency from the parent job A to each of them, and then another dependency from the intermediate job to the final reduction step. So in this way, we've set up a fairly sophisticated task graph in just 3 lines of code. And this is a very useful way to control how data will move from parent to child jobs. We can use input files to specify what's going to move from parent to children, and we can set up workflows in this fashion. So with that, I would conclude, and I'll say that you should certainly navigate to balsam.readthedocs.io, which is also linked from the ALCF user guides. Here we have several tutorials showing more involved examples of setting up workflows involving large parameter sweeps, attaching pre and post-processing scripts, creating dependencies, as well as tutorials for using things like Deep Hyper to explore machine learning models with some kind of search algorithm. We also have runnable demos that right now are located under the SDL workshop directory. but this will be, hopefully by the time the workshop starts, we'll have another location that's accessible to the computational performance workshop participants. So thanks very much, and please do let me know if you have any questions.